and welcome to episode number 6 of CS350 Online. I'm your host, as always, Leslie Eisted, and in today's episode, we're going to continue our discussion of semaphores, and we're going to also take a look at condition variables today. So it should be very exciting. Now, again, just to remind you, if you haven't gotten started with assignment 1, we really recommend that you do so. And you should have all the things that you need to work on assignment 1 by the end of today. So we're going to talk about condition variables and how they should be used today. The other thing is that assignment 2 is going to be available very, very soon for those of you who want to get a head start. And on assignment 2, you are actually going to be asked to implement locks and condition variables. So you will be able to get started on that very, very quickly. And then the quizzes, we have started making them available. So the first 2 quizzes are available, and we should have 2 more available to you over the weekend. So lots of things for you to do. Now let's look at our OS of the day. So today's OS is called DTSS instead of CTSS. And you might be thinking, is this one of those language things where you're like, did they just add one to the letter? Is it like going from C to C++? But actually, that's not what it is. So CTSS, which we covered last class, was compatible time-sharing system. And DTSS is Dartmouth time-sharing system. And what's interesting about Dartmouth time-sharing system, so this is from 1964, and this ran on a GE200 series machine. And yes, GE as in General Electric, the people who make the light bulbs and all that, they used to make mainframes. So this is from Dartmouth College. And this is really the first successful implementation of an operating system that supported time sharing. So it was so successful that it actually remained in operation until 1999. Now you might be thinking, was it the same code base? No, obviously they made a lot of updates and upgrades to this implementation over the years, but this operating system was in operation until about 20 years ago. Now, what made it the large scale success that it was? Well, when they created this operating system, they used preemption for time sharing, and they had this idea that they wanted every user to believe that they were the only one out there. So you are the only user that is using this computer right now, which they thought meant every action or every request you make of the computer should take no more than 10 seconds to respond. So it's the illusion of having your own computer. And they were successful in implementing this. But in order to really, instead of have this operating system just be just some toy that the systems group was using, and maybe a few people in the computing in school, they decided that they really wanted this operating system to be used by everybody. So by 1968, so in just 4 years, they had 80% of the students at Dartmouth using this. And Dartmouth, I mean, they have arts programs, they have all different kinds of programs. So they were finding as many different excuses as possible for the different students at Dartmouth to actually use this operating system. So that's kind of a cool thing. All right. So where did we leave off? We left off, let's go back over here. We left off talking about semaphores. And if you remember, before we talked about semaphores, we talked about locks. Locks are a synchronization primitive that we use to create mutual exclusion. So we have a critical section. We want only one thread to be in that critical section. So what we're going to do is we create a locking door. There's only one thread allowed, so we either are owned or we are not owned. And any thread that tries to acquire the lock, and while the lock is unavailable, will have to go to sleep and wait. But we kind of realize that, maybe we have more than one resource. And that's how we think about semaphores. A lock is I'm only letting one thread into this region. It's that locking door, mutual exclusion. We only have one resource. But for semaphores, stop thinking about things in terms of mutual exclusion and start to think about things in terms of, I'm doing some synchronization with respect to a number of resources. And I can only have people come in and take a resource if there's some available. And that's what a semaphore does. Is semaphores actually have a counter inside. that keep track of how many resources are available. To acquire the semaphore, we call the P function. So we P the semaphore, and Ping the semaphore, if the counter is greater than 0, we will decrement the counter and we will enter the critical section. Otherwise, we are going to wait. We fall asleep. And then V, the release function, is going to increment the counter and wake up a thread that might be waiting for the resources to change. So there you go. We have a semaphore and its P and V functions. And just to remind you that P and V are actually atomic, which means even though the code is multiple lines, you can assume that the behavior of the function is always the same, and that it's, even if it does get interrupted, it's not going to have any impact on the result. We talked about 3 different kinds of semaphores. In particular, we talked about how a binary semaphore is like a lock in the sense that it can be used like a lock, but it is different. So it's just a semaphore with a single resource, and you just P and V like you would acquire and release a lock. The big difference, though, is that there's no restriction. So it is possible for someone to V the lock multiple times and increment the resource counter. And it's also possible in this case to have a thread that does not own the resource release it. So semaphores have no concept of ownership. Then we have a counting semaphore, which is just one with an arbitrary number of resources. And then finally the barrier semaphore, which we actually use to force threads to wait for some event to happen. Oh, excuse me, before continuing. All right. We showed you briefly in the last class how to use a semaphore as a lock, and we also showed you how to use it as a semaphore. And where we're going to continue today is we're going to look at a synchronization problem, a very popular one, that actually uses semaphores to solve. So let's get started with that right away. So there's this famous problem in computer science, or with concurrency, called producers and consumers. And the idea behind producers and consumers is you have some unit that is producing something. So I always like to use the example of a car plant. So if you are Subaru and Subaru has a big plant in Indianapolis, you are going to be producing cars. Now you can't just produce cars ad infinitum, because if you do that, you're going to fill the planet. You have a bounded buffer of places where you can put the cars that you actually are building. And in the case of, a car factory, there is a large parking lot surrounding the factory with a limited number of car spaces, parking spots. So long as there is a free parking spot, you can actually come in and you can make a car and put it there. So a producer is producing resources so long as there is a place to put the resource that you've created. Then you have the consumer. The consumer wants to take something, take a resource, but it doesn't make sense for the consumer to be able to take a resource if there are none available. So in this case, it would be the dealerships coming and taking a car from the factory lot and taking it down to their dealership. And the dealerships, of course, are located all over North America. And if you're up in Aqualit, you don't want to send a truck to pick up a single Subaru if there are no Subarus on the lot, because that's a really long drive. So what we have to do is we need some way of synchronizing this. We want to make sure that producers are only producing vehicles if there's a place to put them. And we want to make sure that the consumers are only coming to take a vehicle if there's actually a vehicle waiting for them. And we can actually use semaphores to provide the synchronization for this. So this is a partially correct solution here. So the first thing that we have to do is realize that there are different kinds of resources for different tasks. So for one, the resource for the producer is the number of empty spaces in the bounded buffer. And at the beginning of the day, the buffer is empty, and so our initial count of buffer items is 0. So we'll create, it's not. there are n empty spaces, not 0 empty spaces. You don't start the day with a full lot. That makes no sense. Sorry. Spaces. We start with n empty spaces so we can produce things. But items, the number of cars in the lot starts out as 0. There is nothing produced. What's going to happen then is in the producer wants to take a space because that's its resource. So the producer is going to P spaces. And if there is a space, the space count will decrement, and then the producer can add an item to the buffer. Now, this is where things get interesting. When the producer added an item to a buffer, he consumed a space resource, but he didn't produce one. He produced an item. He produced a car. So we P spaces to decrement the number of space resources, but we V items to increment the number of cars that are in the lot. So we're going to P spaces, add the item to the buffer, and then V items. And similarly, in the consumer who wants to take an item, we P items, remove the item from the buffer, which produces the resource for the producer, which is V spaces. Now then, there is still a problem with this piece of code. The problem is that while the producers and consumers are effectively sharing the buffer, or at least the producer is never going to produce an item if there's no space for it, and the consumer is not going to be able to consume an item unless one exists, there's still a problem. And the problem is that they might be trying to do it at the same time. So you could have the producer and the consumer both trying to add and remove an item from the bounded buffer at the same time. So we actually need to put mutual exclusion around these two lines here to make sure that only one thread is manipulating the buffer at a time. You could use a binary semaphore, or you could use a lock here, whatever you please, and that would solve the problem. All right. What I'd like to do now is I'd like to take you into the OS 161 source code and show you some of how the Semaphore is implemented. So this is grabbed right from OS 161. All right. So if we look at the P function, remember the code we gave you for lock yesterday, the pseudocode? Now, I have taken out the assertions here, by the way. And the reason I've taken out the assertions was to save space. So this is just the meat and potatoes. The assertions have been removed here. So we need to check the value of the resource. So we're going to acquire this spin lock. This is to do an atomic test and set. While the Semaphore's count is equal to 0, that is, while there are no resources available, we lock the wait channel. Sorry, I'm trying not to sneeze. We release the spin lock, we sleep, and then when we wake back up, we reacquire the spin lock so we can do the check again. Once we are awake, and we know that the Semaphore count is greater than 0, we can decrement the Semaphore's counter in order to indicate that we've taken an object. And then we release the spin lock because we are now done manipulating the Semaphore's resource counter. Now, does this or does this not look awful similar to the lock code? And the answer is yes, it does. It looks very similar, almost identical. And again, yes, I have removed a few extra lines here, assertions and so on, just to save some space. But the body of the implementation is the same. The difference is that instead of setting ownership and instead of setting a held variable, now we just have a resource counter. And the release or V function looks very much the same. We acquire a spin lock. We're going to increment the counter, wake a thread, release the spin lock. So these are very, very similar things, except there's no concept of ownership. Now, a lot of people ask and wonder, why do these 3 lines of code have to be in this specific order? And I tried to explain it a little bit last class, but maybe you didn't catch the answer why. Now, there is a longer explanation on Piazza in the extra notes thread, and you're welcome to look at that. But we're actually going to look at why these 3 lines have to be in this specific order here right now. So let's suppose you have 2 threads, and let's suppose that the count of resources is 0. So thread 1 calls P to try to acquire a resource, and it gets to the line. It checks whether count is equal to 0. It is equal to 0. Let's suppose that the lines of code are in the wrong order here. So instead of having lock, release, sleep, let's suppose we had release, lock, sleep. So this is if the code is in the wrong order. So we verified that the count is 0. We need to go to sleep, so we release the spin lock. When we release the spin lock, we can have a context switch because, of course, interrupts get turned back on. So now thread 2 runs. If thread 2 runs in its entirety and it is producing the resource, it's going to V the semaphore, increment the count, wake a thread waiting on the semaphore, and then once it's done, there will be a context switch back to the original thread. Now, the original thread will release the spin lock under the illusion that the semaphore still has a count of 0, and it doesn't check again. Then it's like, okay, well, I'm continuing where I left off, which means I've got to lock the wait channel and fall asleep. So it locks the wait channel and falls asleep. But here's the problem. When we do it in this order, we are letting thread 2 wake the wait channel before this thread has fallen asleep on it. Which means that thread 1 is now asleep on a semaphore that has a resource available. And who's going to wake it up? Possibly nobody. So this thread might sleep forever. So when we have these lines of code in the wrong order, we let threads fall asleep on resources that are available. We don't want that to happen. When we put the lines of code in the correct order, and if it serves me, I think there might actually be a typo in these slides, and I'll point it out when I get to it. We lock the wait channel in thread 1, and then we release the spin lock. On the context switch, thread 2 can acquire the spin lock. It increments the count. And then in W21 wake 1, it actually has to wait. So it can't actually wake anybody up because the lock of the wait channel is owned by thread 1 and not thread 2. So we end up having a context switch back to thread 1, where thread 1 falls asleep on the wait channel, and then a context switch back to the other thread where W21 wake 1, and this is where the typo is because we should still be in wake 1 at this point. Wake 1 will then wake you right back up, release the spin lock, and now you are in a ready state and you can try to acquire the semaphore again. So when you actually put these in the right order, you are preventing anybody from falling asleep on a resource that is available. Now, another interesting thing you might point out. One of the other consequences of the implementation of OS 161's wait channels is their wait channels are actually implemented with spin locks for protection. Which actually means that if you lock the wait channel here, there won't be any preemption and this won't even happen. So this code here that we have, this trace we just did, is assuming we don't know the implementation of the lock for the wait channel. It might be a regular lock, maybe it's not, maybe it's something else. But if you know that the wait channel's lock is just a spin lock, then actually this context switch doesn't even happen. So it's kind of interesting. Make sure you put those 3 lines in the correct order, and that's going to come into play for assignment 2 when we are asking you to actually implement locks and condition variables. All right then. So what's this thing called a condition variable anyways? Because we've asked you to use them on assignment 2 or assignment 1, but we haven't actually told you what they are. Of course, you can read ahead and all that, and maybe you already knew. Let me describe the problem we're trying to solve. Let's suppose you are in a critical section protected by lock. And the shared variable you're trying to use, let's say it's variable x. And variable x, in order for you to proceed in your critical section, variable x needs to have value 5. But inside of your critical section, protected by the lock, x has value 4. So you can't continue. You need to wait for x to equal 5, but x is 4. Here's the problem. You own the lock that is used to protect variable x. So you need to be able to wait for the value of x to change, but you own the lock on x, which prevents anybody else from actually trying to change x. Another way to think of it is, suppose you go to a bar, and I know nobody can go to bars right now, but let's suppose you're sitting at a bar and you have, a mug. I don't feel like using a mug today. Let's suppose you have a shot glass in front of you. And you pick up the shot glass. That's a big shot glass. And doing so, you have acquired the lock on the shared resource known as the glass. And when you pick it up, you bring it up to take a drink out of it, and you realize it's empty. And you're like, oh. Well, the bartender cannot fill it up if you have the lock on the glass, because it's in your hand, you have it, and the bartender's not going to, reach over you and, pour stuff into it, because that's just creepy and weird. So here you've got the lock on the glass, and you need it filled. What a condition variable is going to let us do is simultaneously release our hold on the glass, put the lock down, and fall asleep. So we fall asleep and release our hold on the lock, which permits the bartender to pick up the glass, fill it, and when the bartender puts it down, he's going to throw it down the top of the bar. I don't know what it's called. He's going to throw it down and throw it down the tabletop, and it's going to knock you in the head, and you're going to simultaneously wake up, pick up the glass, and take a drink. So, what a condition variable lets us do is safely fall asleep inside of a critical section while releasing the lock, so that some other thread can acquire the lock, change the condition, and when they change the condition, they're going to wake us up so that we can then proceed in our critical section. All right. So, how do you use one of these things? Well, our API provides 3 functions. We have wait, and wait is the big one. Wait is going to give us the logic for simultaneously falling asleep while releasing the lock. And the last thing that wait's going to do on leave is wait is actually going to reacquire the lock. So when you enter the wait function, you own the lock, and when you leave the wait function, you own the lock. So we're protected in that sense. Signal and broadcast are very simple. Signal is going to wake up one thread, and broadcast wakes up all threads. We'll talk about the implementation of these in a minute. I'm going to skip. I'm not going to talk about using condition variables here. We are going to go on to slide 45. So let's suppose we didn't have condition variables. How would we do this task? Can we do this task without a condition variables? So let's suppose, and I know nobody's on campus in the spring. It's going to be so weird. This is going to be possibly the first spring, or maybe the second one, because I guess we've been off since March here. But anyways, it's going to be this spring again this year where you don't have to worry about what path you take across campus to avoid all the nesting geese. But let's suppose you had created an app that when you leave your house in the morning, you can ask if it's safe to walk from where you are to your destination. Maybe it's the basement of MC or something. So in order for it to be safe to walk on the path, the number of geese on the path has to be 0. If the number of geese is greater than 0, then it's not safe to go. So in safe to walk, we need to check how many geese there are. And the number of geese is going to be a shared global variable. So we acquired the geese mutex, which is going to protect that number of geese lock or variable. And then we're going to check if the number of geese is greater than 0. But here's the part. We've got to figure out, using just a lock, how do I wait safely? Actually, it's pretty easy to do this. So what you're going to do is you acquire the geese mutex, and then in a while loop, you are going to check if the number of geese is greater than 0. If the number of geese is greater than 0, you release the lock. And the reason why you release the lock is because you want to give an opportunity to another thread to take the lock and change the number of geese. And then after you've released the lock, you're going to reacquire the lock. And this is the thing that gets people confused. Why are we doing that? We have to reacquire the lock because the next iteration of the loop, I need to check whether the number of geese is greater than 0. So before I perform that check, which happens like in this weird part of the code right here, I need to make sure that I own the lock. So we're briefly releasing the lock to give an opportunity for another thread to take it, and then we are going to acquire the lock again to do our next iteration. Now, to improve the performance of this and to increase the likelihood that another thread gets the lock so that we can make progress, you'll often see in between lock release and lock acquire, people will actually use thread yield to encourage a context switch to happen. You can put that there if you want, but you don't have to. So this is effectively a safe way of waiting for a condition to be true inside of a critical section. Yes, I know the lock release is missing its pseudocode, okay? Here's the problem. I'm spinning. So I'm actively spinning on this condition. I am going to keep asking. I'm that annoying toddler that comes over and pats you on the shoulder. Can I have a cheese string? Can I have a cheese string? And then you haven't even checked whether you've got the cheese strings or not in the fridge. So we need a way to make the toddler wait until the number of cheese strings is not 0 before they ask again. We don't want this spinning. And this is what the condition variable is going to let us do. It's giving us a place to wait for the condition to be true. So this is the same code or same function, but now we're going to use the condition variable instead. So we still use a lock because we need to protect the critical section. Condition variables are used in conjunction with a lock. You can't use it without a lock. We still check our condition. Condition variables don't check the condition for you. And that's one of the big misconceptions about the implementation of condition variables is a lot of people think, oh, well, you must have to pass it like a function pointer for it to check what the condition is. No, you are responsible for checking the condition on a condition variable is being used for, and you are responsible for then calling wait or broadcast appropriately. So we're going to say, while the number of geese is greater than 0, I call CV wait. Now you're like, I still have this in a loop, which means I'm still spinning. But you're not. Let me explain. So you call CV wait, you're going to simultaneously release the lock and fall asleep. Okay. That means another thread can come and take the lock and change the number of geese, and then they can call CV signal to wake you up. When you wake up, you reacquire the lock, and you return from CV wait. So at the point where you wake up inside CV wait, you believe the condition is true. But then why are we using this while loop? Because presumably then if we were woken up when we return from CV wait, the condition must still be true. Nope. There's no guarantee of that. Here's the problem and why we use a while loop under this situation. And in fact, while you often see while loops being used with condition variables, this kind of condition variable is called a mesa style. When somebody calls CV signal or CV broadcast and they wake the sleeping thread that was waiting for the condition to be true doesn't start running. In a mesa style condition variable, which is what pthreads is using, by the way, and we are as well, When you are woken, you go to the ready pool, which means you may not run right away, which means that some other thread might run before you and change the condition back again. So, in the majority of cases where you are using a condition variable, you will see, a Mesa style one, you will actually see the condition being checked in a while loop. It is not a busy wait. We are just checking that once we have woken up because the condition changed, that the condition is still what we want, because there was no guarantee that we ran immediately after being woke. The other style of condition variable is called where style, and I don't know how to pronounce that word. It's H-O-A-R-E. And what happens in that style of condition variable, which is significantly harder to implement, I'd like to point out. In the where style condition variable, what happens is when you are woke, the signaling thread is immediately put to sleep, and the thread that wakes up is immediately ran, which means there is a guarantee that the condition is still the same when it starts running, because it immediately started running. But we don't have that style. And if you're wondering, where might I see that other kind of condition variable? I have never used them. Mesa style, I want to say, is like the most popular kind of condition variable. But if I were to use a where style condition variable, I would actually use one for a real-time operating system where I wanted to guarantee response times for when events happen. Because when the condition, let's say you were waiting for you were waiting for the light, or somebody to cross the street, or you're waiting for the street to be clear. You want to take advantage of the fact that the street is clear as quickly as possible. You want to respond to that event very quickly. So where style, I feel, is much better for real-time applications, because you will be responding to the condition changing more rapidly than you would with the Mesa style. All right, now how do you implement this little beast? How do you implement a condition variable? Well, let's take a look. So let's open OneNote here. I know it's going to break on me. It always breaks on me. My laptop is so angry with me, it's actually like being really slow. Okay. Gonna make my window nice and small. Okay. So view. There we go. All right. So a question on Twitch. How does the condition variable know which threads to wake up? So when the condition, so you're going to use either signal or broadcast to wake threads up. If you call signal, you will be calling wake 1. And wake 1 on wait channel, wait channels are implemented as FIFO queues, so it will wake up the oldest one. If you call broadcast, it wakes up everybody. Now, how does the condition variable know it should be calling signal or broadcast? Do the condition changing? Well, it's up to you to check the condition and to actually call signal or broadcast. And another question on Twitch, I apologize for doing these out of order. Does the thread get the lock upon waking up and being put in the ready pool, or when getting run, does it have the lock while in the ready pool? Okay, so interesting story. Our implementation of condition variables is the lazy, old, not so great approach, but that's fine because it's OS 161. So in our implementation of condition variables, we are going to call inside of CVWait, we will call lock acquire. So when we wake up, we are going to get pushed onto the ready pool without owning the lock, and we will have to wait for us to be run before we can actually call lock acquire, before we can actually return from CVWait. Now, one implementation that I have seen for condition variables, and there was a name for it and the name is slipping my mind right now, is to actually do a handoff of the lock. in Signal. So the idea would be that you can improve the performance under certain circumstances by inside of Signal actually handing the lock's ownership directly to the thread that you are waking, so that when it goes into the ready pool, that thread already owns the lock, and so the function will immediately return from wait, owning the lock when it's run. So there's some variation to improve performance there. But we don't do that handoff to improve the performance. We're going to do it the slow, lazy way. So don't worry about that. Anyways, I'm going to talk about CV wait now. And I apologize for anyone at home who might be noticing my things are getting a little grainy and then the color's changing a little bit. So I actually have a great big 6x6 foot window in front of me, and the sun is changing, which is changing how the green screen's behaving. Just a word of note. You shouldn't be filming using sunlight as your light source unless you are actually outside. And even if you are filming outside, you'll find people still use lights. Not that anyone here is doing that, but there you go. All right, so let's look at CV wait. Now, I'm only going to do kind of a pseudocode implementation here. So you have to simultaneously, let's look at the steps. So we want to fall asleep and release the lock. And I want to do that at the same time. And then before I leave CV wait, I want to acquire the lock. So those are kind of the main ideas of what I want to do in CV wait. But how do I do this? Well, first off, what am I waiting on? Am I waiting on the wait channel of the lock? No. In fact, that makes no sense whatsoever. Remember that a wait channel should only contain threads that are waiting on the same thing. And if I use the lock's wait channel to wait for my condition, that doesn't make any sense, because the threads that are on the lock's wait channel are waiting for the lock to become available. If I'm waiting for a condition to be changed, I should be waiting on a wait channel for threads that are waiting for that condition to change. So how we're going to do this is our CV needs a wait channel. And I'm going to short form this to W-chan, just like that. So that's great, right? Okay. What do we do now in our implementation? Now, I'm not going to write any assertions that you need to make. I'm going to assume when you sit down to write this at the beginning of assignment 2, you can figure out the necessary and appropriate assertions. So let's just look at the pseudocode for the body of the code. So I need to fall asleep on this wait channel, and I need to release the lock for the critical section at the same time. So if you look at the CV wait function, it takes a CV and it takes a lock. And the lock that I need to release is the one that is passed in, because it's the one that belongs to the critical section. And then at the end of the function, the lock I'm going to be acquiring is also, it's the lock for the critical section, so it's this lock as well. So let's take a look at a rough pseudocode here. So I'm going to need to fall asleep on the wait channel. And then I'm going to need to release the lock at the same time. But if I release the lock after W-chan sleep, that won't work because I'm not executing code anymore. So I actually need to release the lock here. And then I wake back up, I'm going to need to acquire that lock again. So does this work? Nope, doesn't work. The reason why it doesn't work is we forgot the fact that W-chan sleep needs to have the wait channel locked. So where are we going to lock the wait channel? Right here. So before we release our lock on the critical section, we lock the wait channel. That's preventing all interactions by other threads with the wait channel. And due to the implementation of the spin lock, it's also preventing preemption. Then we are going to release the lock, and then we're going to fall asleep. When we wake up, we reacquire the lock, and we return. So that's kind of a rough pseudocode guide to how to implement CV wait. Now, what about signal and broadcast? If you look at the implementation, well, there's no implementation of CVs in OS 161 right now. You're going to add it, but the API is already there. So you just got to fill in the bodies of the functions. If you look at signal and broadcast in our implementation, you'll see that they take a CV and a lock. And I want to tell you this. You can't remove the lock parameter. You can't remove it. But I don't know why the eraser never works. Yeah, eraser totally never works. So you have to keep this parameter. But, here's the big but. You do not have to use it. So, in reality, when you call signal to wake a thread, you are going to be waking one of the threads on the wait channel using the wake one function. But if you look at the notes for signal and broadcast, it says you need to make sure that you own the lock that's passed into CV signal and CV broadcast. Really? You don't. I mean, you should. You absolutely should own the lock that's passed in, because the lock that you use to protect the critical section for wait, where wait is called, should be the same as the thread or the lock that you are using to protect the critical section when you call signal. Because presumably the wait and the signal are happening over the same condition, the same shared variables. Should. But we don't keep track of what lock the condition variable's been used with. I mean, you could, but we don't. The other thing is that doesn't actually do much for us. So you might be thinking, if I guarantee that it's the same lock, does it actually change what our code looks like? Not really. It doesn't. Because you're still going to need to check the condition in a while loop, because there's still the chance that somebody's going to take the condition out from underneath of you. So it's not really that beneficial to check the ownership of the lock inside of signal and broadcast. Now, should you call signal and broadcast in the critical section that is protected by the lock that you used for wait? Yes, you should, because you want to make sure that when you actually call signal or broadcast, the condition is guaranteed to be true. And it can only be guaranteed to be true if you signal or wake people in that critical section protected by that lock where you change the condition. So, yes, you should own it, but you do not have to check it. Even though the source code that is provided says you should own this lock here, you don't have to own it. We are not going to deduct marks if you choose not to check the ownership of that lock. However, in CV wait, this is different. You must own the lock. And you must check ownership here. Now some people say, but release does it for me. Why don't I just let it fail in release? Well, let me tell you why in CV wait we don't let it fail in release. We want it to fail in CV wait. Because you always want the error or the assertion failure to happen at the earliest point where the problem is detected. So you could let lock release cause the assertion failure. But the problem actually happened in CV wait. You called CV wait with a lock you didn't own. And so CV wait needs to check ownership, but signal and broadcast don't. Yes, you will lose a mark in CV wait if you don't check ownership of the lock. But you will not lose marks if you don't check ownership in signal and broadcast. And there's extra notes provided for this, by the way, on the course website. So if you want to know more, you can. All right, question on Twitch. How can we know which thread the current code is executing on to check ownership? You know which thread is running because it's you. And if you want to compare to see, is the owner of the lock you, there is the lock do I hold function, which you will be implementing. And the lock keeps track of ownership by keeping a pointer to the thread structure. And what lock do I hold does is it will compare that pointer to check if it's equal to the current running thread structure. And that is held in a variable, which I'll write on my notes here. There is a global variable called cur thread. And cur thread is a pointer to the structure for the thread that's currently running. So in lock do I hold, you're going to compare the lock's owner to cur thread. And that's how you will know if the lock and the owner and you are the same. The lock's owner and you are the same. By the way, there's another one called curproc for the current process. But that's for A2. You don't need that for A1. All right. So, we've seen kind of how to implement these lovely little beasts here. Now let's actually solve a problem with them. It'd be nice to actually see how they're used, right? So, what I want to do is actually look at the producers and consumers problem with the condition variables this time. So, before we can do that, we have to think about what we are doing in producers and consumers. What are the conditions? So with semaphores, it's easy to think about because we've got this idea of, to the producer, the resource is the spaces, and to the consumer, the resource is the items in the buffer. But now we're not talking about things in terms of resources. We need to translate that understanding into conditions. So what we're going to do is we're going to have a buffer of size n. N is the max size of the buffer. And then we have a count, an integer count, which is how many things are in the buffer. Here are the two conditions then. If the count is greater than 0, then there's items in the buffer for the consumer. So the consumer has to wait for count to be bigger than 0. And the producer is waiting for the number of items in the buffer to be less than n because it wants to put something in. It wants a free space. So the producer is waiting for the condition count less than n. So to solve this then, let's take a look at our bounded buffer with condition variables. So we've got our shared variable count right here at the top. And again, I know you keep seeing this word volatile, and I think we've explained it a couple times on Piazza. We are going to go into detail as to what this means. We might even get into it today. Wouldn't that be great, right? But for now, just trust me that we need it there. Then we have our lock, and we've got our two condition variables. Each condition variable should represent a different condition. You don't want to have multiple threads waiting on a condition variable, and they're waiting on different conditions. It doesn't make sense. You have one of these things for each condition. Why do we only have one lock, though? Well, because the lock is to protect the shared variable count. We don't need, if we had two locks to protect count, that would make sense. We'd either still have a race condition or have some really, really obfuscated and weird code that might deadlock. All right, so in produce, we need, as the producer, to check the condition. We need to check if the number of items in the buffer is equal to n, because if it is n, then we gotta wait. So I acquire the lock so I can check the count while the count is equal to n. So while the buffer is full, I call CV wait. And I am waiting for the buffer to be not full. So I am waiting for count to be less than n. Now remember, even though this is in while loop, this is not actively spinning. We check the condition, we fall asleep. When the condition changes, we wake back up and we have to validate that the condition is still what we want before we can proceed. Once we validated that count is less than n, we can add the item to the buffer. we increment the count, and by incrementing the count, we've changed the condition for the consumer. The buffer is no longer empty. So we are going to signal, that means wake one thread, we will signal not empty, which is going to wake up a consumer. And then we scroll too far there. We are going to release the mutex. So that's great, right? I think we've got that figured out. And the consumer's code actually looks very similar. So we acquire the mutex, we check if the condition is not being met, and in this case, we're checking to see if there's any items in the buffer. So while there are no items in the buffer, I fall asleep waiting on the not empty condition variable. Once the condition is met, that is the count is greater than 0, I will remove an item from the buffer, I decrement the counter. Now that there is space in the buffer, I am going to signal not full, and then I release the lock. So there you go. There is producers and consumers with condition variables and locks. Now, if you were to ask me, we've introduced you to like 3 or 4 different synchronization parameters. You've got spin locks, you've got locks that block, you've got semaphores, and you've got condition variables. Which ones do I use? I use the semaphores. I use the semaphores almost exclusively because I find them to be exceptionally versatile and easy to understand. Personal preference. Almost every problem that you can solve with one of them, you can actually solve with the others. Which actually brings me to a problem I would like to introduce you to. So, we are not going to take this problem up today, but I do want to introduce it to you today so that you have some time to think about it. So, just give me a minute here. Lost my train of thought. There it is, Sem2CV. Couldn't remember the name of it. So Sem2CV, which you'll find in that archive that I've posted on Piazza, you are given a problem that is solved using 3 semaphores. So here is the code being solved with 3 semaphores. And what we want you to do is change this implementation so that it uses locks and condition variables. And when you are doing that, make sure that you keep the behavior the same. So, for example, if you look at this code here, semaphore A and B actually just behave as locks. Okay. It's semaphore C, which starts out with no resources. You'll see here that function 1 has to wait for function 2 to run before it can go. And each function 1 will have to wait for at least one iteration of function 2 to go before a function 1. So what we don't want to happen is we don't want there to be a backlog of 10 function 1s waiting for exactly 10 function 2s to go through. So as the function 2s execute, some of those function 1s should be let through. So try to implement this with locks and condition variables and global variables, and maintain the behavior of this code. And yes, this is a previous midterm problem. I know you don't have a midterm. We have quizzes instead, but it's good practice. And for the record, if you're looking to study CS350, I would like to point out at this point some resources that you have available to you. Sample problems. You have probably the best resource for midterm and sample problems of any CS course. So if you're on the course website, go to I feel like because we don't have formal exams anymore that we might have actually taken the link off. I don't want to sign in. Okay, so I'm going to have to make sure that this gets posted again. But yeah, I will talk to the maintainer of the website. We do actually have an archive of all previous midterms and solutions, and they are publicly available, and you can access them whenever you want for sample problems. Yes, someone on Twitch says maybe an older offering. So let's actually go to like Winter 20 because I bet we can find it there. Exam information, yes. So if you go to the Winter 20 website, you'll see exam information and you'll see sample exams with solutions. Click on that. And there you go. Look at that. Look at that. It goes all the way back to like when I took this course almost. All these beautiful, beautiful previous midterms with solutions. So you have a lot of resources available to you to do sample problems. And you've even got solutions to check whether you're right. And then if that wasn't enough for you, we also have these review questions. We've got this archive here, and then we've got this archive with solutions here. Now, these were actually produced by a bunch of students and TAs. There are mistakes in them, but there are still lots of great resources in this content. The course has changed a lot since these were produced, so if you see something you're like, what, we had to prove things? Yeah, we don't do that anymore. But just be aware there's some content here that we no longer cover. But I just wanted to point this out that indeed we have a ton of sample problems available to you, not just the ones that I'm doing here. Okay, so just looking at the clock. For those of you who want to get a head start and implement condition variables, I want to show you the test that you actually have available to you for doing condition variables. So if you look at the code for it, which isn't here, so when you are doing assignment 2, the first thing that we're going to ask you to do is implement locks and condition variables. This should only take you 5 minutes. The condition variable code is like 10 lines tops across all functions. And the locks, you can almost copy and paste most of the code from the Semaphore implementation. And that's not considered cheating unless you take it from somebody else's copy. But anyways, take it from your own. So what you're going to do is then, in order to test locks and condition variables, we have some tests. So if you go into test directory, current test, look at the file synchtest.c. And in synchtest.c, we have tests for the locks. But I don't want to show you the lock test. What I want to show you is the condition variable test, because it's kind of weird. So we're going to go to line 261. So this is CV test thread. What's going to happen is there are 3 global variables that we have. We have test val 1, test val 2, and test val 3, and those are global variables. And then what we're going to do inside of this function is we're going to wait until test val 1 is equal to num. Now num is going to be your thread number, which is you. So until the global variable test val 1 is you, you're going to wait. And when test val 1 is equal to your thread number, you're going to sound off with your name, which is your number, and then you're going to change test val 1 to some other thread number. And you'll see a bunch of other stuff in here that's going to validate whether your condition variables are working or not. But what I want to show you is what this test result will look like. So going over here to OS161, I'm going to run this with kernel 1, which actually has condition variables and locks implemented. So locks and condition variable implementation used to be assignment 1. We changed it. So for me, this is the kernel that I have. Oops. Of course, I didn't want the debugger. Okay. So the condition variable test is SY3. And what you should see if you run SY3 is you should see 32 threads sound off in reverse 5 times. So you should see thread 31 to thread 0 print out 5 times. If you see anything else, your condition variables don't work or your locks don't work. So actually, here's the thing. When you're implementing locks and condition variables, you need to ensure first that your locks work. When you are 100% certain that your locks work, then test your condition variables. Because if you don't, and you test your condition variables first, what you're going to find out is that if you have a bug in your lock, how do you know it's the lock and not the CV? It'll make it harder to debug. So how are you going to test the locks? Okay, so let's open up kernel 1 again, and I'm going to show you the test menu. There are 2 lock tests that we run. There's SY2, and there's UW lock test. Do not be surprised if these tests take a little bit of time. Of course, my computer's annoyed, so it's going to take even more time. I've seen these tests take up to about 60 seconds. That's not shocking. So there we go. When you are testing your locks, you should be testing against SY2 and UW1, as that's what we are going to run on. Because race conditions are dependent on the order of thread it will depend on where the context switches happen, running them once or twice isn't going to be sufficient. What you need to do is you need to write a script that is going to run these tests 100 times or 1,000 times and dump the output to a file and then check to make sure that the results are correct in that file. Now, there's going to be this temptation to sit here at this prompt and run tests back to back. But I'd like to show you what happens in OS 161 if you run 2 tests back to back. Of course it works. It shouldn't. But I have a lot more things implemented than you. There we go. I got it to fail. So, OS 161, this is where I have this like evil look on my face. When you call free, nothing happens. You need to call free because when you get to assignment 3, it's going to matter. But for now, when you call free, nothing happens. So there's no concept of freeing memory. There's no reusing of memory. And you don't get a lot of memory to use in this OS. So if you try to run these tests back to back, you will get weird errors like this one. Thread fork failed out of memory. And I've seen a bunch of other ones as well. This is happening not because of something that you did. This is actually happening because of how the OS is currently implemented. You cannot run tests back to back in OS 161. You must shut the OS down and start the OS up again to run each test. And I know with the menu system, that's going to be a pain in the ass. So there's another way that you can do tests, and that's from a command line, and this will make things scriptable. So what you're going to do is you type sys161 kernel, and for you it's going to be ASST2, not 1. And then in quotes, put whatever commands you want to run. So if I want to run sy2, the lock test, and then I want to quit, I do sy2 semicolon q. It will boot the OS, run sy2, and quit. So now you can script the testing of locks. And you can do the same for condition variables. Now you might be wondering, what do these tests look like if they fail? Because, you know, it's easy to see how they succeed, but how do they fail? Okay. Well, let's go to a kernel that I have that doesn't have this implemented. So this is assignment 0 kernel. Let's see what happens. Oh. It succeeded. Well, let's run that again. It failed this time. So here's the thing. The reason why you have to run this test so many times is because if you don't, you might just, by the luck of the draw, every execution of the test, the threads executed in such a way that there was no problem. Sometimes I've actually tried to run this test and it's taken me like 20 runs in order to get the test to fail. So it's really important that you run these tests like 100 times to validate that they're not going to fail. So that's SY2 and it fails. I'm going to let you figure out what UW1 does when it fails. Now I want to show you the CV test when it fails. That's SY3. You get a lot of gobbledygook. So all this junk here, yep, that's a failed condition variable test. So it tends to be a bit more obvious. Okay. So once you have, here's something that you don't know. When you run OS 161's test by default, you are actually running on a single core. And sometimes it takes a really long time for one of these race conditions to show itself on a single core. So we can actually make it easier to show the race condition, if there is one. So after you have thoroughly tested on a single core MIPS R3000, you can increment the number of CPUs you're using and run it again to validate that your code has no problems. And what you're going to do is you're going to open this file, sys161.conf, and go to the very last line. And you'll see here that it says mainboard RAM size, blah, 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 CPUs equals. Change the number of CPUs to something else. And save the file, and then rerun your test. And what you will see is that there's a higher probability of encountering a race condition because now you've got more cores, and so you're opening yourself up to more possibilities of race conditions. And so this can be, the final test. Now, a lot of people are like, why don't I just test with, 4 cores to start with? Because debugging problems with your locker CV implementation on 4 cores is a lot harder than on 1. Test it thoroughly on a single core and then test it on 4. We are going to be testing your code for assignment 2 on multiple CPUs. So make sure you do this. All right. So I think I'm actually going to leave that here for today. I don't usually like starting a topic right at the end. So let's just leave it there. So in next episode, we are going to look at the other 2 sources of race conditions, including what does volatile mean, why do we use it, and what are the side effects from using it. And we'll also look at, how your CPU can introduce race conditions into your code. And we'll take up that sample problem, and then I think we will have an opportunity to start processes. So that's going to be lots of fun, and we'll be doing that next week. So we will see you then.
Don't ever do that again.
This is not one of your games where real people will die, you pathetic little worm.
She was in the mainframe. Check the computer. She's a moron. A 2nd level programmer. She works on the guidance system. She doesn't even have access to the filing codes. Red rocket and firing. What the hell is happening? We have re-entry in 12 minutes.
It did burn up someone over the Atlantic.
Deal with it. She changed the access codes. Then she can fix it.
Go ahead, shoot him. He means nothing to me.
I can do it! I can break our codes. Then get on with it! Tell him, now! Give me the cores, Atalia! Give them to me!